Hello. Now I gotta do it again. Hello and welcome to Calculus 3. So, chapter 12. In order for us to do Calc 3 at all, we have to know about parametric equations and we need to know about polar coordinates. And we are going to use this a lot. So you need to know everything about these things. So let's talk about parametric equations first. So parametric equations. What they do is they separate your dimensions in respect to a parameter that you bring into the picture. If you have your good old two-dimensional equation y equals, let's say, 3x plus 6, that's a linear equation. Or you have, let's say, 3D equation which you will eventually learn. Say you have x squared plus y minus z, or equal to z. There you go. Just keep it there. You have two variables in the first one, and that's 2 dimensions. You have 3 variables in the bottom one, and that's 3 dimensions. So the top one graphs on the xy plane, the bottom one is in the xyz plane, which is the focus of this class. And the parametric equations break these dimensions into x equals function of, let's say, parameter t, you can think of it as time, and y equals some other function, say g of t. This one on the bottom, 3D one, let me just move it a little bit down, would be broken into 3 equations. Say x is equal f of t, y is equal g of t, and z is equal to, I don't know, h of t. So this is what parametric equations do. Now, we will be using these a lot, so you will have a lot of practice. My main goal is to bring this to you as a concept. Now, I want to focus on 2D just to explain the concept, and then we will do a lot of 3D, obviously, throughout the course. Let's say I have y equals 2x squared plus 3x minus 4. There are few ways in which I can work parametric equations for this. The easiest way is to replace x with t. So you set the parametric equation x equals t, and then y is equal to 2t squared plus 3t minus 4. At which point in life you would just say, why? And you'll be 100% correct. You just made something that was already simple worse, right? So absolutely no need to do something like this. But we can, all right? Welcome to math, right? When are these important? They're important in cases where you don't have a function. For instance, x squared plus y squared equals to 9. What is this? It's a circle. So you draw circle, with radius 3. Is this a function? No. Is the derivative for this easy? It's implicit differentiation. Annoying. Can you integrate this? Hell no, right? It's integral of a function. That's not a function. You can't integrate. Can you force integration on it? Sure. You can solve this for y as plus minus square root of 9 minus x squared. Then you can ignore the negative sign, which would only focus you on the upper half. Then you have to double your integral from negative 3 to 3 for this square root of 9 minus x squared dx. Then you have to do trig sub. It's like, kill me now. Kill me now, please. Right? Because you got to do all of that stuff. To find what? Area under the curve? Just use pi r squared and you're done. Right? It's easy. So, if you don't have a function, your calculus already is not happy. Right? Because you take limit of a function, take derivative of a function, you take integral of a function. And when you don't have a function, well, something terrible has to happen, right? Because calculus is applied to a function. Now, what do parametric equations do in this case? Parametric equation goes in and says, your equation for x is 3 cosine t, or theta, let's use theta, and your y is 3 sine theta. Well, that's great, because I just went from something that is not function into a pair of functions. So now I can integrate, I can differentiate, I can do stuff easy. So are parametric equations good for everything? Hell no. But in some cases, parametric equations are way to go. Now, when we move to the 3D space, parametric equations are always the way to go. So for 2D, useful sometimes. For 3D, extremely useful. And some of the sections will solely depend on your ability to move in this framework. Now again, we will learn when we get there. That's, you're not supposed to know it now. Another example of this is the general, what's the circle? The general shape of a circle is? Circle is a special case. What's the general? It's the same deal, like square and rectangle. Ellipse, thank you. X squared over a squared plus y squared over b squared equals to 1. And then you draw ellipse. And then you have your A and you have your B. Oh, okay, now I see the way the projector, so you actually cannot see. So the last 3 rows, whatever I have on a screen, you don't see on the, okay. All right, fine. I'll have to keep that in mind. The projector is not mounted right. Okay, so ellipse. You see that you have a major and a minor radius. And what happens if those are the same value? If A is equal to B equals to R, you get the circle, right? Because both of these are going to be R squared. That's the common denominator, puts these together, and then R goes there. You get a circle, right? So ellipse is the general case, and the circle is just a special case when these two are the same. So what are the equations for this then? Well, your parametric set is x equals to A cosine theta and y equals B sine theta. So earlier you had R and R for circle, now you have A and B for ellipse. Now, what I did not mention before, and now I have to add it, I'm going to go back and add it as well over there. You have to specify the range for theta, or domain of theta. 0 to 2 pi to draw entire image. Okay? Now I'm going to go back to my circle, and if I want one pizza slice out of this, what is my theta? Nope. That's 2 slices. Pi over 4. One slice of pizza, when you cut, you get 8 slices. One slice of pizza is going to be from 0 to pi over 4. So if I want the full circle, I will specify theta to be from 0 to 2 pi. If I want half of the circle, 0 to pi. If I want one pizza slice, it's going to be 0 to pi over 4. Right? You go to those kids' parties and knowing 0 to pi over 8, right? So, what, you don't go to the kids' parties ever?
No, to a small piece of pizza.
Yeah, I know. But then they're also small kids. And they go give them like a slice that's more for me. So, yeah. I used to bash on that, not anymore. I thought about it. So, parametric equations allow us to go from something that it's not a function into a set of functions, and then we specify the domain, and we can do a lot of cool stuff with it. So we're going to express a lot of things later. You guys know what a spring is, right? You took a pen apart at some point and just went, right? So the spiral, it's called a helix. There is an equation for that in math. And we're going to learn that equation in Calc 3. It's going to involve this for x, this for y, and then another equation for z, and you will create a spiral that goes up. So to figure out location in space in 3D, we'll be using sets of 3 equations. Again, we'll learn that when we get there. Right now, I need you to be masters of the 2 equations. Now, when you have a parametric set given to you, let's say x is equal to t plus 3 and y is equal to t squared minus 4, you can put these equations together and you can create an equation in your xy realm, right? So you go to the first equation, you say t is equal to x minus 3, then you plug in, then you suffer with algebra, y equals x minus 3 squared minus 4. So that's your bottom equation. And now you FOIL this, thank you. X squared minus 6x plus 9 minus 4 to get x squared minus 6x plus 5. So basic algebra gets you to where you want to be. In case that you have the circle equation or the ellipse equation, let's say x equals 3 cosine theta and y equals to 4 sine theta. What is this? This is an ellipse. Great. Is this one horizontal or vertical? Vertical, because your y has a larger radius, right? Y has a larger radius, x has the shorter radius, so this one stands up, right? It's 8 units top to bottom, it's 6 units left to right, so it's vertical. Now, these are a little bit more annoying. Your cosine theta is x over 3, and your theta is inverse cosine or x over 3. Some of you might learn this as arc cosine, depending on which school you came from. So whether you're going to write cosine inverse or arc cosine x over 3, whatever you put, I'll understand. Okay, so you use your notation that you are comfortable with. Now, you will plug this there, and we will have y equals 4 sine of inverse cosine of x over 3. And now you would remember these problems from all the way trig course, right? You had to solve these. It was a homework assignment. Now you see why. Welcome to parametric equations. The way to do this is to rewrite cosine inverse into a sine inverse using the triangle. That's the trick. And then they cancel. So you use your triangle. That's a terrible triangle. The right angle, angle theta. Cosine is adjacent over hypotenuse. So x and a 3, which would make this one 9 minus x squared, if you use Pythagorean theorem. So adjacent over hypotenuse, adjacent over hypotenuse, and then you do Pythagorean theorem to get c squared minus a squared is beast, right? So now we have y equals 4 sine, and now we write inverse sine, and inverse sine is going to be square root of 9 minus x squared divided by hypotenuse, which is 3. This is the time when these guys die, sine and inverse sine, and we have y is equal to 4/3 times the square root of 9 minus x squared. So you move 4/3 to the right, becomes 3/4 y is equal to square root of 9 minus x squared. You square both sides to kill the root. It becomes 9 over 16, and you have a y square on top is equal to 9 minus x squared. Is anyone nauseous yet? No? All right, good. We move x squared to the left. 9y squared over 16 plus x squared equals to 9. Multiply through by 16 over 9. No, I lied. Divide by 9 everywhere because you want 1 on the right hand side. So divide everywhere by 9. So divide by 9, divide by 9, divide by 9. 9 and 9 would cancel. You get y squared over 16 plus x squared over 9 equals to 1. X squared over 9 plus y squared over 16 equals 1. So this is what we call mathematical gymnastics. We see that we can transform these parametric equations back into your Cartesian equations that you are used to. And that's that. So now we have the way to go back and forth. Parametric equations are not unique. You guys will come up with different parametric equations, unless you all use just the basic form. but they are not unique representations, so you can come up with other stuff. So let's say you have x squared plus 6x minus 9 is equal to, no, it's just y equals, or f of x equals, right? And one way would be to, as I said before, say x is equal to t, and then y is equal to t squared plus 6t minus 9. This is the cheapest way you can achieve it, and it's completely useless, right? More creative ways are to make equations easier to deal with, because these equations are the same, right? So you haven't achieved anything. But if you complete the square over here, over 100,000 videos on how to complete the square on YouTube, I will mention that. If you complete the square, you would get y equals x squared plus 6x, half of this is 3, so plus 9, minus 9, and then a minus 9 from there. Y equals x plus 3 squared minus 18. So these two forms are the same parabola if you complete the square. And now I can make this x equals so I want to make t to be x plus 3, which means x needs to be t minus 3, and y will be, so this is my set. This is what I need. Y would be t squared minus 18. So as you can see, parametric equation set is not unique to the problem. Everyone can come up with their own representation. And if you do this, now your representation here is different than that one, but it's still the same equation. So that's a story of parametric equations. One more important aspect of parametric equations is, since you have an extra parameter added, right, the theta or the t or whatever you want to call it, that allows for one more degree of freedom, so you can get something out of it. And that will be the motion. It will be orientation. So parametric equations, in addition to the shape, also give orientation. If I write x equals r cosine theta, y is equal to r sine theta, then I have a circle with the radius r moving counterclockwise. If I write x equals r sine theta and y equals r cosine theta, I have the same circle, radius r, this time moving clockwise. So orientation is simply which way the graph will flow. If I have theta equals 0 on the top picture, theta equals 0 will give me this point here, because cosine of 0 is 1, so you have x is r, and sine of 0 is 0, so it kills the y value, so you have r comma 0, right? That's going to be on x-axis. So you have your first point to be there. If you pick your theta to be pi over 2, you are going to get the top point. Theta is equal to pi over 2. Pi over 4 would obviously be there in the middle. So you see the progression in time. Theta equals 0, pi over 4, pi over 2. So it's going to rotate counterclockwise. For the bottom picture, if you go theta equals 0, well, you're going to get theta equals 0 on top. Because x is going to be 0, sine of 0 is 0, and y coordinate will be r. That's that one. And now, for theta equal pi over 2, you will have this point here. And then theta equals pi, all the way on the bottom. So you see that the motion, the flow, right, as you progress with the higher values of theta, it will progress in a clockwise way. So just by swapping x for sine for cosine, will change the motion, which way it goes in parametric equations. Now, every set that I had before has this feature, orientation. Parameter t can be regarded as time. T equals 0, initial position, initial location. So t equals 0, you plug in 0, you plug in 0, 0, negative 9 is the location where the world starts, right? T equals 1, well, x is equal to 1, and y is equal to negative 2. That's the next point, right? And since t went from 0 to 1 to 2 to 3, these points that you line up on a graph will give you uniquely which, right, because you know which point you draw first, which point you drew second, which, right? So as you go through that, it goes all the way up to infinity. And you have orientation. You can put the arrow. Now, that's going to be very important for us because I mentioned that helix, you want to know whether the, let's say, eagle is going helix up or the eagle is going helix down. You can do the end, whatever, I don't care, right? Because we want to trace the motion in 3D, orientation will be very important. The change in height will be governed by the third equation that we don't know yet about, but whether the eagle goes up or down will be solely which one is on x and which one is on y. Because your helix, right, when you look at at the spring, like the top, all you see is a circle, right? You don't see the zigzagging stuff. Right? When you look at it from the top, all you see is a circle. So you only see these two dimensions when you look down. Now, when you look from the side, you see that circle progresses up or progresses down, and it will progress in a way which you flip these equations. Yes?
Wouldn't, like, that helical path that you're talking about, wouldn't it progress upwards or downwards based off of the z function? And the sine of that?
You can switch it there as well.
Okay.
But you also switch it on the sine and cosine. So you have to be careful.
Okay.
And the z equation can be linear, which gives you the linear rise. It can be quadratic or it can be exponential, right? So you have the wheel, right? So you can, all of that will be, you can custom all of that. And then you can obviously use it in engineering to create different springs and different, right, things. So that's parametric equations. And we are going to see this very soon in a different setting, but I will tell you, this is nothing but parametric equations written differently. We want to put that into a vector, and we'll go from there. The second part that we need to review, it's called polar coordinates. So if you guys never learned about polar coordinates, this is your last chance. Before you have to upgrade it to 3D coordinates. Polar coordinates, the coordinate system r, theta operates in a circular environment. So what you are used to, I'll write this as old, which is rectangular coordinates, also known as Cartesian. Coordinates. This is what you are used to. You have your XY graph or XYZ graph. If you did AutoCAD or whatever, you know exactly what I'm talking about. And to locate point 5, 3, you have to go 1, 2, 3, 4, 5 units on x-axis, and then you rise 3 units up to get to your 5, 3 point that you want. So the first coordinate is x, second coordinate is y. We always put x and then y, and we count out x, then we count y. If you have a negative sign, you would change the direction in which you're counting. For negative x, you go to the left. For negative y, you go down. You are well aware of this coordinate system, and you've been using it for a decade at least of your life. Now, we are introducing something new. It's going to be a coordinate system where you move in a circular fashion. So now, I'll call this new polar coordinate system, r, theta. I should put over here x, y, so we know what we're talking about. In the polar coordinate system, you will draw the radius and then swing that radius or the angle that it's given to you. So 3 pi over 4, you will go out to 3, and then that's your pi over 4 angle. You will swing this pi over 4 to get to 3 pi over 4 coordinate. Cool? What happens if you have negative 2 pi over 3? Well, now you will draw negative 2 as a radius. Now, positive angles are always counterclockwise. You have to go down. Pi over 3 is 60 degrees, approximately here. And you will swing this negative 2, and this will be your negative 2 pi over 3. What happens if you have a negative angle? 4 negative pi over 6. What now? You tell me. go out 4. Okay, I agree. Clockwise, great. We're going to go down pi over 6, that's 30 degrees, so that's about there somewhere. We're going to swing downwards, and that point is 4 negative pi over 6. All right, so what do you need to remember for polar coordinates graphs? We go positive r, we go negative r, we go positive theta, we go negative theta, we go negative theta, we go positive theta. There is no such a thing as draw on a y-axis and then, no. Polar coordinates are always off of the x-axis. You are allowed to have positive or negative radius. You are allowed to have positive or negative angle. This diagram is completely useless because, I mean, it shows everything, but you know that the negative numbers are left, positive numbers are right. You know that the positive angles are always counterclockwise, and the negative angles are always clockwise. So, completely useless, but at least it shows everything. Well, it's a good time to go, why? Why polar coordinates? We were happy with x and a y. Yes, we were completely happy. Can we do something else with these? And the answer is, oh yes, right? If I go to Cartesian coordinates, right, and I say x equals 3, what would that graph? X equals 3.
Straight line.
Straight line up and down. We call that vertical line through 3, right? So we're happy there. And the other basic equation is y equals, let's say, 2. What would that give me?
Straight horizontal.
Straight horizontal line through 2. Excellent. Now I'm going to make these lines red. So these are the basic equations that you get in the rectangular world. Now, one thing that I would like you guys to consider here is that equation is x equals to 3. Is y mentioned at all in this equation? No, right? And y takes all of the values from negative infinity to positive infinity. We see that, right? So every point on this line is always 3, something, right? All of the points. 3, 0, 3, 1, 3, pi, 3, negative e, 3, whatever, right? So all of the values are there for y. Y is not mentioned in the equation at all. We have the same happen here. X is not mentioned at all. It takes on all of the values. So your equation is always something, 2. All of the values are in there. So now I want to know, for polar coordinates, what are my basic equations? What do I get when I say r equals to 4? What would that graph? What do you think? keeping in mind that when you get the equation like this, and there is no mention of theta, theta is taken from negative infinity to positive infinity, you will run through all of the values. What happens?
Just a
Circle with radius 4. Yeah. I wanted to do this.
You mean like a lanyard?
Yes, because if I take this and I just flip it like this forever, right? That's going to be infinite theta. It takes all of the thetas. It's 0 to 2 pi to make one revolution, but as I do like this forever, right? It goes on forever. So all of the thetas are there. This is a circle with radius 4. So why are we excited now? Why are we all jumping with joy?
Because you don't need x and y to make it
Yeah, but what is the equation for this in x and y?
x squared plus y squared equals
And what do I know about this?
16.
Yeah, radius is 4, so 4 squared 16, right? What do I know about this?
It's impossible
We
to
can't
do.
integrate.
Yeah. This is terrible. Derivatives, integrals, everything is terrible about it. Look at this. How cute is this? It's like when you're walking down the street and you see the little dog, right? Like the white one, whatever it's called. What's the little white dogs?
Pomeranian.
Pomeranian, thank you very much. For the second time. Pomeranian, right? You just want to like eat it or something. No, not that. It's like, no, we're not in Korea. You know what I mean, right? It's like so cute. It's really cute. Compare this to this. There's no comparison. There's absolutely no comparison. We want to deal with this, and we definitely do not want to deal with that, right? So this is what polar coordinates do for us. They create these equations that we can deal with, right? And both of these equations describe exactly the same picture. Come on, we can take the derivative, we can integrate, we can just dance circles around this one, right? It's r equals to 4, come on, right? How about theta equals to pi over 3? What do we get? You have to take all r's in consideration, from negative infinity to positive infinity. So
Straight line.
a straight line through 0 at the angle of 60 degrees. Excellent. So that's pi over 3 angle, and it's a straight line through the origin. Is it easy to have a straight line going through, let's say, a 4? No, it's a nightmare. Okay, let's keep exploring. By any chance, do you have your TI calculators with you? If not, don't worry about it. No, correct, you can't see anything. Now I gotta do all of this again. No. Ah, perfect. Functions in polar coordinates, that's exactly what I wrote. Functions in polar are r as a function of theta. So I said functions in polar coordinates are r as a function of theta. That's what I wrote. So now I'm going to graph r equals 4 sine of 4 theta. Yeah. It's a basic trig function. And what do we get? We get a flower. How cool is that? Now I'm going to change the 4 into a 5. I'm going to change 5 into 8. Going to change 8 into 2. We actually specify the number of petals that we want. And if you do this enough, for practice, you quickly pick up that anytime you have an even number, you get twice as many petals. Every time you have odd number, you have that many petals. So if I put 9, how many I'm going to have? 9. If I put 8, how many am I going to have? 16. Exactly. So you pick this up. Now, you pick this up quickly. Now, if I change sine for a cosine, I'm going to rotate the flower on axis. So cosine, it rotated. If I change 2 to 4, how many petals I'm going to have? 8. Exactly. So you see that when you have a polar function, r equals theta, it gets you something like this. Now I'm going to go back into sine. Sun? No. This is probably a sign. It's probably my son is logged out of Minecraft screaming at home. Let me just check. Where's the technology? Nope. All right, good. There we go. So this is our 4 sine 2 theta. I'm writing y equals 4 sine 2 theta. And we all see what it looks like. The theta in here is from 0 to 2 pi to draw the entire shape. How much is one petal in terms of thetas? And this is a trick question because I am a terrible person. You are tempted to say 0 to pi over 2 because that will be a quarter, right? So we'll do 0 to pi over 2. You were right. Why am I still gloating? Because I can change this into a cosine, and you don't get it this time. So what should I do? I should go from pi over 4 to 3 pi over 4. Now I get one petal. So there is some experimentation that you have to do with these guys, okay? You are not used to this stuff. So we still have pi over 2 interval to draw one petal because we have 4 petals, but they're not necessarily 0 to pi over 2. As you can see right? You have pi over 4 to 3 pi over 4. So there will be some experimentation for you to figure these things out where they... Now, what is this good for in Calc 3? Baking. You have a stencil in this case, and you press that into a cookie dough. What is the volume that you get out of that cookie dough? Well, you're going to integrate in polar coordinates, which will actually upgrade to the 3D called cylindrical coordinates. So you get to integrate this, and you get the volume of the cookie times the number of calories per, right? And you get to write the nutritional facts on it. People are contracted to do these things and paid money. This is what it's used for. If you want to have a flower stencil. Is there a heart stencil? Sure there is, yes.
So do cylindrical coordinates just add height to that then? To the
yes, it will be r theta z.
Okay.
We will have spherical coordinates built up on this as well, r theta phi, which would add another angle. So you need to know your polar coordinates well in order to add the third dimension to them and make them triplets, like x, y, z, which is this class focusing on. That's not going to be a problem. We are in a box. X, Y, Z. We don't have to use any brain cells, right, on that one. But now your flowers are going to become your XY domain on the floor, and then Z-axis for cylindrical or another angle, theta, which will be measured off of the Z-axis. I'll do arm wrestling later when we get to the chapter on when we need that. And we'll upgrade. All of these concepts are fairly simple. It's just that you don't have a lot of experience with this stuff. We're not even talking any kind of calculus here. We're talking barely middle school, calculate points in a cosine, right? And just draw the thing. It's just, to get a little bit familiar with these things, you have to just trace a few of these by hand. Now, what else do I want to talk about here is this idea of why we have this stuff. If I want to convert between two systems, Cartesian, which is rectangular, and polar conversion, I'll do this conversion here. Keep in mind what we have. We have a point here that it's either given as xy or is given as r theta, but it's the same point. Please note that every time that I drew earlier any of the polar stuff, you see how I have x and y on axis? I don't have r and theta on axis. All of the graphs that I drew, xy, 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 all of them. So the r theta is not a new coordinate system, it's a new way to get to the point. New way. So now my dimensions over here are x, ry, and r, and angle theta. How cool is that? So now I can write 3 trigonometric functions and the Pythagorean theorem, and those will be my conversion equations, right? Can I write sine theta? Sure I can. What's sine theta? Very good. What's cosine theta? Excellent. What's tangent theta? Y over x. Good. What's Pythagorean theorem? Perfect. I gave you enough time. So when you write these for just sine, cosine, and tangent, and the Pythagorean theorem, it gives you conversion equations. I'll switch to blue. Y equals r sine theta. If you have r and theta, you can calculate y. And here, if you have r cosine theta, you can calculate x. This is clearly conversion from polar to rectangular, because you have both r and theta, and you are getting your rectangular one at a time. That should be common sense. The bottom one, theta is equal to inverse tangent of y over x, and r is equal to square root of x squared plus y squared. There's your conversion from rectangular to polar, because you have x and you have y, and you can calculate r and theta one at a time. So with these conversion factors, you can conversion equations, you can go either way. The question is, do you want to go? And most of the time, no, you don't. These two systems do not compete for territory, right? They don't have any quarrels, because each one of these operates in their own domain. We already seen that this equation here gives us that beautiful fourth petal flower, and it was very simple. We have our just sine equation. Beautiful, right? Oh my, I said y equals, holy nightmare. R equals, please fix that. R equals, not y. So r equals 4 sine 2 theta. Amazing. Can we rewrite this in xy? Of course we can. Let's do it. You're probably already dreading, and you are right to dread it. R equals 8 sine theta cosine theta. I just used the trigonometric identity for sine 2 theta as 2 sine theta cosine theta, and then 2 times 4 is 8. Now I am going to swap in r is the square root of x squared plus y squared. It's disgusting already. 8 times, the sine is sine theta. Sine theta is given as y over r. So that's y over square root of x squared plus y. Oh, kill me now. Times x over square root of x squared plus y squared for cosine. It's shaping to be beautiful already. Square root of x squared plus y squared is equal to 8xy divided by square root and square root multiply into just this. Now we'll clearly multiply both sides by x squared plus y squared, which would give you x squared plus y squared to the 3/2 is equal to 8xy. You want to solve this for y? No, you won't, right? You can't. So that, or r equals 4 sine 2 theta. You can do that game, like when you go to the eye doctor, like what's better, A or B? You know, just keep moving, A or B, A or B. If you've never been to the, you just missed out on it. So do these compete? No, they don't compete. They don't compete because clearly this is infinitely better than that. Now, if I go and pull off something like, we don't have to go far. Y equals 3x plus 6. I put this one like 15 times today. Try to move this to polar coordinates and it's just hell breaks loose right away. Polar coordinates are not for straight lines and squares and these things. Polar coordinates want these curves and round things, and the Cartesian coordinates want sharp corners and straight lines. So each one is the master of their domain, and just don't force it. That's the rule, right? I mean, you can if you like pain, there's no problem. But what's y? Y is r cosine theta. So y is r sine theta is equal to 3r cosine theta plus 6. Like, you look at this and you just want to cry. There's nothing you can do with this. It's just garbage. So keep Cartesian equations Cartesian and keep polar equations polar. And then when we encounter integrals in chapter whatever now, 17 or whatever they moved it to. Is it 17 or 16? 16. When you run into an integral of e to the x squared plus y squared plus blah 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 or whatever, you say, oh, this could be e to the r squared, and then I'm going to have r dr d theta, and wow, I can just use basic u sub with this thing over here. Is going to be terrible. So there will be instances in this class when we will use polar coordinates to make our integration, let's say, simple. But you do not want to force these conversions if you don't need to. Keep the polar in polar realm, keep the Cartesian in Cartesian realm, and if we must, we convert this. Now, the last part is integration in polar coordinates. And this is important because we are going to upgrade this twofold to cylindrical and spherical. I already said that. And we need to know integration in 2D, which gives us area, so that we can eventually upgrade it to 3D and even 4D to calculate. We are going to deal with 4D as well, because you are going to have distribution of temperature or density or something in a third-dimensional object. So you have your x, y, z to describe the object, and then you need another variable for temperature. Well, that's 4D, right? So we will venture into those realms in this class. But in order to get there, we first have to conquer this stuff. So integration, and this is just 2D. So we are looking at the area. Now, the integral that if you took Calc 2 at RV, the integral that you need to know at this point for area is 1/2 integral alpha to beta of r squared d theta. And now I'm just going to put here aside that r is equal to f of theta, so that's your function. So you can also learn this formula as 1/2 integral alpha to beta of f of theta squared d theta. So I don't care which one you use. I'm just going to go like this. Yeah. Same. So I don't care which form you are going to use, you just need to know it. does this make sense dimensionally? If you paid attention in Calc 1, you learned that area is given as integral a to b of f of x dx. If you paid attention in explanation, you know that this is the limit as n goes to infinity of the summation of 1 to n for f of ci times delta x. Times delta x. So this was your one rectangle, this was your many rectangles, this is your infinitely many rectangles for exact area. Remember that you were cutting those rectangles between A and B, and one rectangle was just a representative rectangle. That's your FCI delta x. F is the height, delta x is the width. So now, when you consider your Calc 1, will I ever be able to spell it? Oh, I'm spelling with C's instead of K's. That's why it's annoying. If you consider your Calc 1, you see that your height times the width, that's the two dimensions, and then you keep adding infinitely many of them, so you add, and when you add all of them, you have exact area. The important aspect is that this is your height, this is your width, and that is the 2D, which is the area. Area is 2D. You have an object that has x, that has y, and area is x times y. 2D. Is this equation in blue two-dimensional? You already have two dimensions here. Isn't that r the length? Yes, r is the length, right? R times r is already the length. d theta is not a dimension. dx is a dimension because dx is the width. dx is the width of the representative rectangle in Calculus 1. So that's going to be your x coordinate, and then your f of ci is the y, right? Because y equals f of x. So you have delta x on the bottom, and then f on the top. X times y is area. Over here you have r times r. That's already 2D. d theta. Theta is not a dimension because theta is not a unit of length. Theta is the angle. Arc length s is r times theta. Theta is arc length s divided by r. If I have a circle and I have a pizza slice over here, and this is my s, and this is my r, the theta in here is arc length s in inches, let's say, divided by radius in inches, and when they cancel, theta has no dimension to it, which is why theta does not bring a dimension to this calculation. Therefore, all of your dimensions are contained within r squared, which means it's area. It's dimensionally correct. Great. Now, why do we need d theta? Well, alpha and beta are angles of input which will tell you how much of a pizza slice do you want, right? Usually, right, when I'm at a party, I eat anywhere from 2 pi to 4 pi, depending on how long I stay, which is 1 or 2 pies, right? The pies are not equivalent, whatever. So now, if I want to calculate area of the circle, R equals capital R, 3, right? Circle is radius 3, radius 5, whatever. So I'm just going to call it capital R. If I want to calculate area of the entire circle, I'm going to have my alpha start at 0 and beta end at 2 pi because I want the whole circle. But if I want one pizza slice, it's going to be 0 to pi over 4. Because, you know the wedge that holds the door, right? The pizza slice, the wedge that you cut out of cheese. Maybe you want to make a wedge as a skateboarding ramp or a skiing ramp so people can break their hips and necks, right? These things are, right, you specify the angle at which you want it. Because the full circle is going to be 2 pi. If you want a slice of that, you will have to specify how much you want. So if I want to find the area of the circle, and I know nothing about Greeks, all right, and their formulas, I just go and I say, okay, 1/2, 0 to 2 pi. I'm integrating whatever your radius you give me squared. You want 3, you want 5, just plug it in. D theta. And there you go. So now 1/2 integral of r squared in respect to theta. What is it? Yeah, you're thinking hard, but if I had 3 squared, which is 9, and I ask you what's the integral of 9 d theta, you would be saying what? No, that's the derivative. You would say 9 theta, right? So it's going to be r squared theta, and theta is calculated from 0 to 2 pi. So now you have 1/2, well, you can say r squared halves of 2 pi minus 0. It cancels. Pi r. Hey, we just proved the Greeks were right. 2,000 years, right? We had to wait like, what, 1,700 years for calculus to confirm their result. They got it with a stick and rope. Right? Talk about 1,700 years of development of mathematics so we can confirm their result. Amazing, right? So, next time you're tutoring someone and they say, you know, what was the equation of the circle in the area? Oh, pi r squared. And they say y. Please. You show off right away. Now, can we calculate the wedge? Sure. One pizza slice, your beta becomes, right? Beta becomes pi over 4. That becomes pi over 4 here, pi over 4 here, and then you compute the value. So you would obviously have the value for r as well, and so on. Calculate the one petal of the flower area, or the entire flower. If I ask for one petal, and I give you 4 theta, how many petals do we have? 8, right? So if I gave you 4 theta, you have 8 petals. You calculate 0 to 2 pi. Whatever area you get, you divide by 8. You give me 1 petal, right? 3 petals out of 8. You divide by 8, multiply by 3, right? So you can play these games. Other cool pictures that you can get with these parametric and what do you call them? Polar coordinates, right? Involve all kinds of other stuff. I like to do the heart function. Or heart curve. How cool is that? It's not that cool because it's just terrible image, but you can't really tell what the equations are, but using parametric and polar coordinates, you can come up with any of these hearts. That one is the best, right? But all the other ones. This is called cardioid, and this equation over here is r equals 1 minus cosine theta. So that's what you can get just writing 1 minus cosine theta in polar. Cheap as hell, right? Because it's easy to get into hell. There's no like tickets and stuff. The other ones, here you know parametric equations, whole bunch of polar equations. So just type in heart function at home, and you can go on and calculate these things and graph them yourselves. A lot of cool images. This is Batman. People have time. Okay. Not as much as they used to, but yeah. Yes. So you can get technically anything. Here's the equation, the exact. Talk about 3D modeling, right? There's a lot of stuff. It should become weird eventually, so that's what the Discord is for. So you just keep posting there, all right? So you have a whole bunch of things that you can do with polar and parametric curves. Integration of these will yield area. And now we're going to do one more thing, and we're done for the night. We will start Calculus 3 tomorrow at 13.1, 13.2. So we just need to talk about now with area when we intersect two polar curves. So in Calculus 1, you learned area under the curve when you have a single f of x. In Calculus 2, or Calc 1, depending on which school you go to, you learned area between two curves, f of x and g of x, right? You find the area between. So now, with this equation that we covered, and I did this proof for pi r squared for the area of the circle, you know the way to find area when you have one polar curve. But what do we do if I have, let's say, a flower intersected with a circle, and I want the area, or I intersect that cardioid, that almost a heart thing, with a circle or with a flower, what is the area that we get? Because, again, you need to know that, because later you are going to run a cylinder into something. And then the question is, what is the volume of that? Where your domain on the base will be the polar coordinates where the two polar images intersect. So you need to practice area between two curves. Now, area between two curves is simply r that is further away squared minus r that is closer by squared. So area between two polar curves is going to be 1/2 alpha beta f squared of theta minus g squared of theta d theta. You can also know this as capital R squared minus lower r squared. All right, so just to show the diagram here, you are probably used to representative rectangle when you when you do your area between two curves. Now we have representative pizza slice because you have d theta, right? D theta is infinitely thin angle. So if I have, let's just intersect two circles. If I intersect two circles, their intersection points are these. And this angle here is angle alpha, and this angle here is angle beta. Now, I'll write this in blood. To get alpha and beta, we set two equations equal to each other. And then you have to solve trigonometric equation. If you're not good there, well, it's lights out. So you know what to practice, right? So let's get an example from the textbook, solve that example, and then go into the night. Pitch black outside. All right, we have example here. It says circle intersected with the cardioid. These things are not as easy to draw. There we go. Maybe I should draw the circle. Let's draw a circle red. Well, now it's hard to draw the circle. Yeah, let's say this is perfect. The circle has equation r equals to 1. And the cardioid, the black one, has r equals 1 plus cosine theta. And this is where they intersect. So now, to find the intersection points, I have to... Where's mine? Okay. I have to set the two equations equal to each other. So 1 is equal to 1 plus cosine theta. Oh, by the way, what are you expecting to get?
A value.
A value. Which ones? Looking at the graph, what are you expecting to get?
Pi over 2.
Pi over 2, which would be this one, and 3 pi over 2, and I heard minus pi over 2. Okay, let's see what we get, right? So these are just looking at the picture, right? You're using your eyes and you look at it. You are expecting pi over 2, or you're expecting 3 pi over 2, or negative pi over 2, something. So let's see. This is cosine theta equal to 0. Hey, when is cosine theta equal 0? At pi over 2 and 3 pi over 2. But it's also at negative pi over 2. So all of you were right. Which ones do you pick? Depends on orientation of these things, right? What do you want? Do you want this one over here? Do you want, right? So it depends what you want. So let's draw a representative pizza slice That's not its mathematical term, that's what I call it. Representative pizza slice. It's like when you go to a party, it's just like infinitely thin for the kids. It's like, you know, can't even see it. So that's representative pizza slice. I'm looking for this area over here. All right, so I see my options over here from negative pi over 2 to pi over 2 to 3 pi over 2 to 5 pi over 2. Obviously, we're not going to use it. We have to use something. We're definitely using pi over 2. There's no question about that. I just don't know which one is this yet. Now, I'm setting up my integral. I have my half, I have the integral, and I have the... now I need to see what's the outer function, what's the inner function, right? Remember what I said. Far minus close. What's far? Black one is far, right? What's close? Red one is close. So 1 plus cosine theta squared minus 1 squared. You still have to put all of that in parentheses because there is times d theta at the end. All right, that was right. That was good. Now, I need to know these guys, right? What's gonna be there? Like which one goes where? What's the best guess? Well, clearly from negative pi over 2 to pi over 2. That would be the best guess, but hold on. Let's verify it. I want to, first of all, circle. R equals 1. All of the values for theta over there are useless because it has all the values, right? We have to focus on the black function. And I want to know, where am I on the black function when I plug in negative pi over 2? Where am I? Right? So when I plug in negative pi over 2, I get cosine of negative pi over 2, which is still pi over 2, right? And how much is cosine of pi over 2? 0. So radius 1. So I placed negative pi over 2, which is this value here, right? That's negative pi over 2. Going clockwise. Negative pi over 2. When I placed negative pi over 2, I got 1. R equals 1. That's a good R for me, because I know this is negative 1 here. So that's a good R. It's a good length. It's 1. So I have negative pi over 2, and it gave me this bottom point. I'm happy. How about positive pi over 2 on top? Does that work? Well, sure. Cosine of pi over 2 is 0. 0 gives me a good length of 1. So we're good to go. So this is the way to set up the integral. And now all we need to do is to compute this. 1/2 integral. Okay. It's going to be 1 plus 2 cosine theta plus cosine squared theta minus 1 d theta. Why is there a sad face over there? Anyone?
Maybe to use like trig rules.
Yeah.
Because that's what it works.
You cannot integrate cosine and sine squared unless you know the power reducing formula. And if you don't know that one, then it's lights out. So cosine squared theta is 1 plus cosine 2 theta divided by 2. And without this formula, you just can't do this problem. 1/2 negative pi over 2 to pi over 2. 2 cosine theta plus 1 plus cosine 2 theta over 2 d theta. And this is equal to 1/2 integral negative pi over 2 to pi, no integral anymore, now I'm integrating. 2, what's the integral of cosine? Sine theta, plus integral of half is 1/2 theta, plus integral of cosine is sine 2 theta over 4, because the 2 from here gives you a half and the 2 that was there. 2 times 2 is 4. Calculated from negative pi over 2 to pi over 2 equals, and I just put this. What does this mean? Just do. Good night. Calculus 3 tomorrow at 7:30 in this room.